Hello everyone, my name is Tom. I'm currently a postdoc at the University of Cambridge. Today I'm happy to present our work OESense, which is co-authored with Andrea and Cecilia. Earables is a kind of wearable worn on human ear, which has been seeing a rising wave in recent years. Manufacturers such as Apple and Samsung have continuously released different types and versions of wireless earbuds. And it seems that this trend is still unstoppable. Gartner's forecast that the market for earbuds will keep growing, and in 2022, earbuds will constitute 35% and become the dominant device in the wearable market. Current smart earbuds are not just aiming for entertainment. Equipped with different sensors, they actually play an important role for a myriad of human sensing applications. As shown in the graph, being worn on human ears, they can sense from the upper part of the body, which complements the sensing scope of other wearables like smartphones and smartwatches. There are two sensing elements, so they can be either fused for improved performance or redundant for better robustness. Moreover, due to the close distance to human brain, earbuds are potential to measure different human signs for healthcare service. In this work, we focus on human motion sensing. So we first look at the sensors equipped on existing earbuds. The most widely available one is a microphone. So to assess whether microphone is a good sensor to measure motions, we record the microphone signal under 5 activities and found that while running can be clearly detected, other light activities such as drinking, chewing are the same as being still. Moreover, we repeated experiments under a noisy environment with music playing and found that all the activities are buried in the music signal. So microphone is not a good option. Some high-end earbuds also equipped with accelerometers. So we repeat the test with accelerometer and found that, unsurprisingly, accelerometer can detect more activities easily. However, due to the movement of human head, accelerometer data will be interfered. So accelerometer have some issues to guarantee the robustness. Instead of trying to tackle this interference, in this work, we propose another approach for accurate and robust human motion sensing with earbuds. The core idea is the joint use of an in-ear microphone and a phenomenon known as the occlusion effect. This graph explains what is the occlusion effect. Our body motions will generate some sound or vibrations that propagates in the body through bone conduction. In normal case, the bone conduct sound in the ear canal will escape from the opening. But if we use an occlusion device such as earbuds or your finger to block the opening of the ear canal, there would form a cavity between the occlusion device and the eardrum. As a result, the bone conduct sound in the ear canal will be trapped in this cavity, and this cavity will result in an enhancement of the low-frequency components. So the motion-induced sound could be clearly captured by an in-ear microphone. So we built a prototype to validate this idea. Basically, we customized on a very cheap wired earbuds, moved the built-in speaker to the outer end, and inserted an inward-facing microphone near the ear tip to ensure a good signal quality. Then, a Raspberry Pi and an audio codec is used for data recording. Here is a demo video shows how the prototype detects human walking, which also compare with the external microphone. The green curve is for external microphone that captures the air conductor sound, while the blue and red curve are for the two in-ear microphones. As you can see, the in-ear microphone have much stronger signal than the in-ear one. This video shows how the in-ear microphone responds to finger tappings on the face. The idea here is that finger taps will generate vibrations that will propagate to the ear canal, and then amplified by the in-ear microphone. Different tapping positions result in different propagation paths, so we can observe distinct patterns on the signal. Next, we validate the robustness of in-ear microphone against background noise and head movements. and this graph indicates that it can effectively deal with this interference. This idea was tested on 3 motion sensing applications: step counting, human activity recognition with 5 activities as mentioned earlier, and gesture interaction with 12 gestures designed by tapping 12 different spots on the face. We then proposed a signal processing pipeline. For step counting, an envelope-based counting algorithm is used after the low-pass filtering. For activity and gesture recognition, we further extracted some audio features and used typical machine learning classifiers for classification. We collected a large dataset with 31 subjects to do the evaluation. For step counting, we considered different ground materials and working scenarios and collected 52,000 steps in total. For activity recognition, we collected 465 minutes data overall. For gesture recognition, each gesture is performed for 60 samples and around 21,000 gestures in total. In the evaluation, we first compared the performance of OESense with accelerometer and external microphone-based approaches. As expected, OESense outperforms both sensors in all the cases. Then we evaluated in details. These 2 graphs show the step counting performance for walking on the tile and carpet respectively, where the bars in each graph is for different walking scenarios such as walking with barefoot, slicker, sleeper, and walking during speaking and chewing. What we can observe is that we achieve 99% recall on average, with the worst case is for walking on the carpet while chewing, but is still higher than 97.5%. The reason is that chewing also creates some spikes that might cause false positives. For activity recognition, we train a model for each individual. This graph shows the average performance. The left and right earbuds have similar performance, and 5% improvement is achieved by fusing them. We also did the leave one out test to see whether there is a general model for all the users. Specifically, we trained the model with data from 30 subjects and tested on the remaining one. The results are shown in the right figure. We can say the model works well for some people, but not for the others. To solve this, we try to personalize the model by adding some user samples for training. And this works well. As you can see, by adding 10 personal samples, which can be collected within 25 seconds, we can improve the performance by 9%. For gesture recognition, considering the user may not accurately memorize all the 12 gestures, we also test the performance with a 7 gesture set and a 5 gesture set. The results show that we can achieve 93%, 96%, and 97% for the 3 gesture set. Another question we asked is whether our system can be concurrently operated with the main functionalities of earbuds, say music playback, without any material interference. Using walking as an example, this figure shows the microphone signal without music playing, and the steps are clearly distinguishable. However, if we play a music with the built-in speaker of the earbud, the walking signals are completely overwhelmed by the music. But the beauty of this work is the occlusion effect, which only amplifies the low-frequency sound that we are interested in. So if we apply a low-pass filter with 50 Hz cut-off frequency to the signals in the second graph, we will get a clean step signal. As an evidence, the last graph plots a spectrogram of the second figure. We can say that the energy of music resides in the higher frequencies, while the steps are in very low frequency range. So our system is compatible with music playback. Finally, we test the system performance of OESense. We implemented a signal processing pipeline on the Raspberry Pi and deployed the pre-trained models. Then, a USB power meter was used to measure the character draw and power consumption of the system on the different operations. The idle Raspberry Pi already consumed a lot of power, and running the whole pipeline consumes additional 750 milliwatt power. We also measured the latency of different operations like low-pass filtering, audio feature extraction, and inference. We found that most of the time is consumed on feature extraction, and the whole pipeline can be done within 50 milliseconds, showing that it can be operated in real time. Here we also discuss some limitations of this work. The first one is high power consumption. 700 milliwatt power consumption would not be acceptable for wearable devices that is powered by batteries. However, given that we have a standard signal processing pipeline, we believe with specialized audio chips and dedicated PCB design, the power consumption would be significantly reduced. The second one is about the safety issue, because our system requires a good sealing of the ear canal opening, which reduces the user's awareness about the surrounding environment. One potential solution is to follow the transparency mode on AirPods Pro, like we can record the environment sound with the external microphone and replay it using a built-in speaker. In summary, in this work, we proposed the joint use of occlusion effect and an in-ear microphone for motion sensing. We prototyped OESense and developed sensing pipelines for step counting, activity recognition, and gesture recognition. We demonstrate the exceptional performance of our system for 3 applications. Also, we assessed the power consumption and latency of the system. Lastly, I'm in the job market at the moment and looking for a faculty job with focus on ubiquitous computing and sensing all over the world. For more information about my research, please visit my homepage and feel free to drop me an email if you have positions available. Much appreciated, and I'm happy to take questions.